So may I begin?
Oh yeah, please start whenever you want.
Okay, so okay, thanks. So I'd like first would like thanks to the organizer for giving me a chance to my recent work. So today I'm gonna talk about time-dependent entanglement entropy in some expanding universe. So because I wanna describe this expanding universe in holographic setup, so I try to make some gravity dual of the standard cosmology. So p-brane gas geometry is some kind of gravity dual of some usual standard cosmology. So I explained that the more details of this p-brane gas geometry. So this work is based on some recent work with my collaborator, Dr. Jung-hoon Lee. Okay, so first, oops. Okay, sorry. Okay, so first I discuss about some motivation why I consider this p-brane gas geometry and time-dependent entanglement entropy. So entanglement entropy is some very important concept to understand some quantum nature of some physical system. So entanglement entropy measures how closely quantum some state of two systems are entangled or quantumly correlated. So definition is some manifest. So this is some definition of the usual quantum field theory. So we first consider some system, which is some pure state, and then we divide this pure system into a two part, A and B. So in this case, so if we trace out one part of the subsystem, then the remaining part is described by some reduced dense matrix. So that's the reduced definition of the reduced dense matrix. And then using this reduced matrix, we can define some von Neumann entropy, which is called entanglement entropy. So this is a definition of the entanglement entropy. So in this case, so there are two subregions, A and B. So we divide these two regions by some border of A. So we call this border is the entangling surface. So entangling surface is a border of the two subregions A and B. So in this case, the entanglement entropy SB, if we trace out the A region, then the entanglement entropy of B describes some quantum entanglement between the A and B. So in this case, so an observer living in some B region who cannot get any information from some region A. So this is some typical definition of the entanglement entropy. Oops. Okay. So this definition of the entanglement entropy is very similar to some black holes entropy. So usually we call that the summer entropy, right? So so similarity of between the two entropies is coming from some very similar feature of the entanglement entropy and some black holes entropy. So for example, so when you define this entanglement entropy, we say that some observer living in the region B, so cannot receive any information from A. So this is very similar to the black hole. So if you consider black hole, so A is the inside of the black hole, then some observer living in the region B, so he cannot get any information from the inside of the black hole. So this is similar to the some entanglement entropy definition. So in this case, the black hole horizon is identified with the entangling surface of the entanglement entropy. So in this, so furthermore, this black hole and entanglement entropy has a very shows the similar important feature. So usually summer entropy is some extensive quantity in usual some thermodynamic system, but black hole doesn't. In the black hole case, the Bekenstein-Hawking entropy is not extensive because which is not depend on the volume, which is depend on the area. So that is an important feature of the some Bekenstein entropy for the black hole case. So entanglement entropy also shows the area law instead of rather than the some volume law. So this is a very similar some similarity between the black hole entropy and entanglement entropy. So because of this similarity, some people try to understand the black hole entropy in terms of entanglement entropy. So additionally, some Liu and Takanaga proposed some new formula to calculate the entanglement entropy in the holographic setup. So that is the Liu-Takanaga formula. This is very similar to the some definition of the Bekenstein-Hawking entropy. So this is just a proposal. And then so Maldacena and his collaborator proved that this Liu-Takanaga formula is really some correct some definition. So in this case, so entanglement entropy, to divide the usual entanglement entropy of the quantum field theory, we call this some holographic one as a holographic entanglement entropy. So holographic entanglement entropy is defined as the area of the minimal surface. This minimal surface is extended to the some dual some geometry, which is a one-dimensional higher some geometry compared to the boundary. So in this case, so okay, so this is our definition, usual definition of the holographic entanglement entropy. So in this case, so this part is bulk and the graded region corresponds to boundary. And we divide the boundary into the two parts, A and B. And then we integrate out or some trace out this region A. Then this gives the some entanglement entropy. In the some from the dual geometry point of view, this tracing out corresponds to some the area of this minimal surface. So that is the definition of this Liu and Takanaga's formula. Okay, this definition is very, very successful and so easily generalized to the other dimension. Okay, so also this holographic entanglement entropy gives rise to some expected picture of the entanglement entropy. Also, it gives us some very important information about some dual field theory. Okay, so what's that? So we first consider some two-dimensional conformal field theory. So this two-dimensional conformal field theory is very special because for the two-dimensional case, so the conformal field theory has so infinitely many conformal symmetry. So moreover, this two-dimensional conformal field theory has a modular invariance. So this large symmetry so allow us to calculate the entanglement entropy so exactly. But in a higher dimensional case, even in the some higher dimensional conformal field theory case, so the conformal symmetry is finite and there is no some modular invariance usually. So usually it is not easy to calculate the entanglement entropy in higher dimensional case. But 2D case, because due to some large symmetry, so we can exactly calculate the entanglement entropy on some field theory side. So this is some summary of the two-dimensional result. So we consider some finite system, and we divide this finite system as a two-part, and then integrate out or trace out one region. Then we obtain this type of So these types of entanglement entropy. Also, we can consider infinite size system. So in that case, this entanglement entropy is reduced this one. So if we take capital L indicate some size of the total system. So when L goes to infinity limit, so this finite system, the entanglement entropy, this finite system is reduced this one. Also, we consider, we also compactify the time direction. Then we also describe some finite temperature case. So finite temperature case, so beta is inverse of the temperature. Then the entanglement entropy at finite two-dimensional conformal field theory at finite temperature is reduced, is given by this one. So this is also related to infinite system. So if we take, let's see, okay, so the subsystem, because in the finite temperature case, we are considering some time direction. We replace L by some I beta. So using some weak rotation, then this entanglement entropy is reduced, this finite temperature entanglement entropy. Also, we consider some non-conformal theory case. So if there is some mass gap, which is the inverse of the correlation length. So in that case, the entanglement entropy is reduced this form. So this is some known example, some result of the two-dimensional conformal field theory. So using this, applying this Ryu-Takayanagi formula to some dual geometry, which is given by some three-dimensional, some A space or some A black hole, like a BTG black hole. So in that case, we can calculate the area of the minimal surface. Then following some Ryu-Takayanagi formula, so this result can be exactly reproduced from some holographic setup. So in that sense, so the Ryu-Takayanagi formula is very successful in two-dimensional case or three-dimensional gravity theory case. However, if we consider some higher dimensional case, then unfortunately, we have no exact result for higher dimensional conformal field theory case, except for some free theory. So as I mentioned, so usually it is not easy to calculate entanglement entropy in higher dimensional case, but in a holographic setup, we can easily calculate the holographic entanglement entropy even in the higher dimensional case. So this is the holographic calculation is very useful when you investigate some higher dimensional, the entanglement entropy of the higher dimensional theory. Okay, so there's so this two-dimensional example provide many some evidence of evidence of some Ryu-Takayanagi formula. So entanglement entropy shows some important features. So it contains many important information. So I summarize some important information, some feature of the entanglement entropy. So first one is the area law. So usually entanglement entropy follows the area law. So this area law is coming from some short distance correlation around the some entangling some surface or some border of the two region. So in this case, so A indicates some short scale or some UV cutoff. Then, so entanglement entropy has a many terms, but the reading term usually proportional to the area of the entangling surface. So this is because of the short distance correlation. And then also there are some sub leading finite terms. So in this case, usually so existence, due to the existence of the UV cutoff, we need some renormalization of this entanglement entropy. So this entanglement entropy usually depend on the some renormalization scheme. However, so there exists some universal term in this subleading finite term, which is independent of the renormalization scheme. So this universal term gives some important physical information to us, so which is independent of the renormalization scheme. So one thing is so it depends on the some dimension, but it's called some C theorem. So Zamorodkov claimed that some C function is always monotonically decrease along the some algebra. So this entanglement entropy shows these types of C theorem. So in the odd dimensional case, this C theorem is changed to F theorem, for example, 3-dimensional case. And 4-dimensional case, this C theorem is, there are some several different types of anomaly term, A type and C type. So entanglement entropy, so holographic entanglement entropy shows that the A type anomaly is monotonically decreased. So this is some important feature, but this is the story in a time-independent case. But so we also apply this entanglement entropy to the some dynamical system. So there are several some example. So one is the so related to this holography entanglement entropy, we have some several important issue. So one is the this one. So entanglement entropy is related to some algebra in a real space, because the entanglement entropy description, the energy scale is given by the length, length of the real space. So because of that, the entanglement change of the entanglement entropy, depending on the some subsystem size, is very similar to the some real space algebra of the some quantum field theory. So using this algebra, so we can some reconstruct the dual geometry from the data of the entanglement entropy. So there is a very some promising some work. So yeah, so this is a very interesting thing. So Lamstone and so many people try to reconstruct the dual geometry from the some information of the entanglement entropy. Okay, so this is one thing, and some another thing is the second thing is, so we can consider some black hole formation. So black hole formation is a time dependent. So this in the holographic viewpoint, this black hole formation is dual to the some summarization of the dual conformal field theory. So we can discuss, well, so many people studied some black hole formation in gravity theory, and then we interpret this black hole formation as some summarization of the dual conformal field theory. So, in this study, people show that the entanglement entropy is so usually evolve because the system is time dependent. But finally, so this entanglement entropy approach to the some black hole entropy. So if the black hole is formed, then the entanglement entropy is evolved to the some black hole's summer entropy. So this is some interesting related to some summarization of the some quantum field theory. So another thing is we can also consider some time-dependent entanglement entropy in some different setup. So if we consider expanding universe, the space-time is expand, then the space-time is a time-dependent. So in this system, we can also consider entanglement entropy. Then, because the background geometry is time-dependent, entanglement entropy is also time-dependent. So why we are considering this expanding universe? So when you consider some cosmology, so there exists some natural, some entangling surface. So usually we call that is a horizon. So when the universe is expanded, so one observer cannot see some outside of some specified region. So that is called some cosmological horizon. So because of this one, so we can consider some entanglement between some visible universe and invisible universe. So divided by these some horizons. So why this is interesting? So usually, so horizon implies that the two region is causally disconnected. So that implies that so classically we have no any correlation between these two regions. However, so if we consider quantum correlation, so quantum means it's a non-local correlation. So we can also get some information from some outside of the horizon, because this at the quantum level, so visible universe and invisible universe are correlated. So that is the reason why so we are studying some time-dependent entanglement entropy in expanding universe. So using the quantum entanglement entropy, then we can get some time-dependent entanglement entropy, even two system is causally disconnected. So that is some main motivation. So we are considering the entanglement entropy in the expanding universe. Okay, so this is the motivation. So now I try to calculate the time-dependent entanglement entropy in say expanding universe. So to calculate that time-dependent entanglement entropy, we first construct the holographic dual of the standard cosmology. So I first describe how we can make some holographic dual of the standard cosmology, and then I calculate the entanglement entropy in the brane world model, which is some dual of the standard cosmology. Okay, so I summarized so compared to some holographic model, I summarized the important feature of the usual standard cosmology. FLRW geometry, we can describe the some expansion of the universe. So depending on some matter contained in universe. So using this FLRW metric, then the expansion of the universe is described by these two equations, Friedmann equation and continuity equation. So in this case, so some continuity equation is determine the density of the matter, in terms of some equation of state parameter of the matter. So that means depending on the matter, so expansion rate of the universe is changed. So exact the expansion rate is determined by some Friedman equation. So if you consider matter is the ideal gas, then we finally obtain these types of result. So expansion rate, the scale factor is given by, so depend on the some equational state parameter of the matter. So there are some important results. So in inflation case, this is some vacuum energy of the universe. So in that case, the equation of state parameter is given by -1. And radiation case, radiation means, so this is a massless field. So in that case, equation of state parameter is 1/3. And matter case, so this is a massive particle. So this gives equation of state parameter 0. So if we consider more some matter, so let's assume that some universe contains some one-dimensional extended object, which is called cosmic string. Then the equation of state parameter of this cosmic string is given by -1/3. And domain world, so this is a two-dimensional object. If we consider this domain world, then the equation of state parameter is given by -2/3. So this is some equation of state parameter determined in the standard cosmology. Then depending on this equation of state parameter, so the scale factor shows us some dependent time dependence. In inflation case, the scale factor is growing exponentially, but the other case, usually the scale factor shows the power of behavior. Okay, so this is a standard cosmology result. Now we try to make some holographic dual of this standard cosmology. So to make a standard cosmology, we can consider two different some holographic model. One is the boundary model. So this is related to Tetra's talk. So in this case, in the boundary model case, we consider.
Sorry, sorry to interrupt. I sent you some wrong messages. It's 20 minutes to the end of the talk.
Okay, 20 minutes.
In my chat, there was something wrong. So.
Okay. Yeah, thank you. Okay, so boundary model case, we first consider some time-dependent bulk geometry. Then, so because the bulk geometry is time-dependent, so boundary is also time-dependent. So this time-dependent boundary geometry can describe the expansion of the universe if we are lives in some boundary. So in this case, we should use some more generalized some holographic technique, which is called Hubeni-Rangamani-Takayanagi formula. So this is sometimes called covariant formulation because it should contain some appropriate time dependence. So this is one case. And we also describe some expansion of the universe in a different setup, so which is called brane world model. In a brane world model case, we consider two bulk space, and we divide this two bulk space by some brane. Then the bulk space is still static, so there is no any time dependence. But the brane dividing this two bulk space can move. So that's some setup of the brane world. So in that case, the motion rate, some motion of the brane gives some time-dependent universe to an observer living in some brane. So this is a two method. So here I using some brane world model because, as I mentioned, the background geometry is static. Still, we can use the RT formula instead of the HRT formula because the bulk geometry is static. So in this case, brane world model case, the time dependence coming from some boundary condition, not bulk solution. Okay, I will show them more details. Okay, so we consider some A-day space, and this 2 A-day space, asymptotically A-day space, is divided by some one-dimensional lower brane. So we assume that we are living, on this some brane. Then we can describe this setup by introducing 2 bulk action and some boundary action. I mean, some brane section. So in this case, we assume that symmetry is continuous, but in this case, so there is some problem because, okay, so for simplicity, we applied some G2 symmetric. The left-hand side is the mirror of the right-hand side. Then we can calculate the extrinsic curvature at horizon. So when from the left-hand side, we obtain this K mu nu extrinsic curvature, and from the right-hand side, we obtain K mu nu 2 extrinsic curvature. But in this case, at this brane, these 2 extrinsic curvature is not the same because the magnitude is the same because we are imposed G2 symmetry, but the direction is opposite. So I mean, there is some additional minus sign. So this is because extrinsic curvature is defined by some normal vector. But in this case, the direction of the normal vector is opposite. So because of the opposite direction of the normal vector, so extrinsic curvature of the both side has some additional minus sign. So this implies that at the brane, this extrinsic curvature is not well defined. However, so we can explain this match of the extrinsic curvature. So because we consider some brane, so if brane has some energy momentum tensor, then the mismatch of this extrinsic curvature is same as the energy momentum tensor of the brane. So this is a continuity equation of the extrinsic curvature at the brane. So this is called junction equation. So this junction equation is to determine some radial motion of the brane. So, okay, so this is the detail. Let's see. So if we consider some bulk geometries given by this form. So this is some most general form, especially if we consider A-day space, then C is given by the R square. Here R means the radial coordinate of the A-day space. Then junction equation is a reduced this form. And also, so in this case, if the brane is moving, then so usually R is depending on the time. So we define the cosmological time of the boundary. Then this A-day metric reduced to this boundary. So this is some induced metric on a brane. So this is very similar to some FLRW metric, right? So if A is usually matched some standard cosmology, then so this brane world model gives some holographic dual of the standard cosmology. Okay, so this is some brane world model. So now we try to realize the standard cosmology in the holographic setup. So to describe the standard cosmology, so we should consider some appropriate matter, some universe. So we, in the holographic dual theory, we also consider some appropriate bulk matter. So let's see. Okay, so if we consider some zero brane is a zero-dimensional object, which is extended to time direction. So zero means only spatial so number of the spatial dimension. So if we consider zero dimension and assume that this zero brane is located at the center of the A dash, then the band reaction of this zero brane gives rise these types of metric with this black ring factor. So this is a typical metric of the A dash black hole. So here, so this part and this non-trivial black ring factor is depending on this brane gas, so zero brane gas. So if we consider zero brane, then we obtain some usual A dash black hole. So in this case, we also find the junction equation. Then junction equation is given by this one. So here, sigma C is given by this value. This is some critical tension. So in this case, let's first consider m equals 0. So there is no any zero brane. Then so sigma is the tension of the brane. So if the brane has some critical tension, then the right-hand side is 0. So that implies that, so here R dot is 0. So here R means the position of the brane. So if the tension has a critical value and there is no mass, then the brane does not move. So usually, so this gives some static universe to an observer living in some brane. However, if m equals 0, so there is no any matter, but sigma is different from the critical tension, then so this gives rise to this types of scale some brane position. So interestingly, this brane position is corresponding to scale factor on the brane. So this is exactly the same as in eternal inflation. So this types geometry. So yeah, so sigma is some tension, some brane tension. So this is the usual place role of some vacuum energy on the brane, right? So if we only turn on the sigma, then we can expect that we obtain some digital type cosmology. So now we consider the effect of the zero brane. So we take assume that a brane has a critical tension, and so there's a non-vanishing mass. So mass corresponds to, so this is a zero brane mass, so black hole mass. So in this case, we obtain this junction equation. So this here, so in this case, the power, the right-hand side is exactly the same as the power of some radiation. So because it is known that the black hole mass corresponds to the excitation energy of some other joint matter on some dual field theory side. So this is a well matched. So if we consider some different matter, so we can consider some one brane gas. So in this case, one brane means it's some open string. So open string is attached to some brane. Then to an observer living on the brane, we see that some particle only the end of the open string. So this behaves like particle, and the mass is given by the length of this open string. So because this is some very long length, long string, so the end of the open string corresponded to some massive particle. Also because of due to some pattern factor, so this particle corresponded to fundamental particle. So so one brane in the bulk geometry corresponds to particle on the brane. So also massive particle. So this one brane gas, so if we consider gravitational bang action of this one brane gas, we obtain so these types of solution. So it allowed us some analytic and exact solution. Only dependence compared with some ADS black hole, it has a different power. So this is black hole case, it's a 4, and string case, this is a 3. Because black hole, when you consider black hole, we consider 0-dimensional object, but when you obtain this one brane gas geometry, we consider some 1-dimensional object. So this is depending on the dimensionality of the object. So this is generalized to any some p-brane gas. Then so if we generalize this some previous one brane gas geometry, then we obtain these types of solution. So here, okay, sorry, G is 1 over R. So here, so if we consider 4, then so this is some general some p-brane gas geometry when you consider some p-dimensional p-brane gas, some ADS space. Then so on this background, we also find some junction equation. If brane has a critical tension, then junction equation is reduced this one. So in this case, interestingly, 4 minus P is corresponded to the equation of state parameter of the matter. So comparing some previous Friedman equation, we find that the equation of state parameter of this p-brane gas is matched to this one. So we understanding this one because so we consider some p-brane which is extend to some radial direction of the ADS. So to an observer, an observer living on a brane, he detects some p minus 1-dimensional extended object. When you consider p minus 1-dimensional extended object, so the equation of state parameter is given by this one. So this equation of state parameter is perfectly matched with some junction equation. So when you consider p-brane gas, the junction equation exactly same as the Friedman equation of the standard cosmology. So p-brane gas describe the standard cosmology. So, okay, so I skipped that. And then, so now we consider some time-dependent entanglement entropy in this setup. So we first consider time-independent case. So this is some typical ADS metric. And we consider so disc-shaped entangling region. And then we can calculate the minimal surface. So in this case, we obtain these types of entanglement entropy. So as shown here, so L squared omega, so this is a reading term, L squared times omega, this is corresponding to the area of the minimal, entangling surface. So this entanglement entropy, as I mentioned before, so shows that the area law. So this is a static case. So if we consider time independence, when you consider some brane world model, then only difference is this brane can move the radial direction. So the boundary condition is given on this brane because the brane can move, so boundary condition also move. So the motion of the radial motion of the brane is depending on the time. The boundary condition should be also in the depending on the time. So we can apply the same calculation with only different boundary condition. So G bar, in this case, G bar indicate the position, radial position of the brane. Then, so we consider the brane position depending on the time. Then this describes some time-dependent entanglement entropy. So G bar, when you consider some brane motion, so if we consider same eternal inflation, then G bar shows this behavior. So in this case, G bar corresponds to one of the scale factor. So using that one, we finally obtain this entanglement entropy. So this is some rate time behavior. So when tau goes infinity limits, so the first term is the reading term, and the higher order term is exponentially suppressed. So we consider this rate time behavior. Then here, so this is a proportional L squared omega 2. So this is the some area times e to the h tau. So this is corresponding to the square of the scale factor. So this is the area when you measure the area of the entangling surface in physically. So yeah, so because the space-time expand, the length is given by AL. So this term is also proportional to the area of the entangling surface. So even in the some time-dependent case, this result shows that entanglement entropy follow the area law. So this is some inflation case. So we also consider some p-brane case. So I show that this is the final result. So if we consider some power law expansion, then scale factor, depending on the time like that. We also, in this p-brane, we calculate the entanglement entropy in this p-brane gas. Then this is corresponding to the entanglement entropy in expanding universe, which contains p-1 extended object. So in this case, entanglement entropy also given by this one. So this is also same as AEL squared times omega 2. So this is exactly the area of the entangling surface. Okay, so here I show that so the dual geometry of the standard cosmology. So I constructed some holographic dual of the standard cosmology by using some brane world model. So in this case, I show that the entanglement entropy in the rate time error, the reading part is also satisfied the area law. We also consider some several different types of cosmological horizon. Yes, because of the time limit, I skip that. Okay, so that's all. Okay, thank you very much.
Thank you very much for this interesting talk. And now it's time for questions. You can raise your hands. Probably that's the most efficient way if you have any questions. And so maybe I can ask one. So what comes next? I mean, what possible development do you in this?
Oh yeah. Let's see. Yeah, so I skipped the main field. So the main goal is we want to consider some horizon. So there are some two different types of horizon: cosmological or particle horizon and cosmic event horizon. So for example, so if we consider particle horizon, then we are here at this time, but we cannot see the outside of this part. So only we can see this region because the light velocity has some finite value. So because of the finiteness of the light velocity, we can see only the finite region. So these two regions, visible and invisible, is causally disconnected. So there is some classical correlation because some classical information cannot move faster than the light velocity. So there is not any correlation at the classical level. However, if we consider some quantum correlation, then we can obtain some non-trivial correlation, because quantum correlation is usually non-critical, non-local. So in that case, we find the entanglement entropy shows some different time dependence. Also, if one interesting is if you consider cosmic event horizon, then so this is a result. Entanglement entropy have finally approached to some finite value. So this corresponds to the thermal entropy of the digital space. So this is some story in a digital space. So we can see that the entanglement entropy evolved to some digital, the thermal entropy of the digital space.
Thank you very much. If there are no other questions, then let's thank Dr. Park again.
Okay, thank you.
Then,